Today's topic is transforming quadratic equations, and you can use the date of May 7th. Your note packet should have 3 pages. In previous lessons, we've talked about parent functions. We did this with lines and with absolute value functions. We also have a parent function for a quadratic equation. So the simplest quadratic equation is simply one term. It's actually an incomplete quadratic. You'll notice in the diagram y equals x squared has a turning point at the origin. It's equally spaced around the y-axis and it does open up. This is the standard form of a quadratic, and other quadratic equations will have other terms present. When you add the other terms, this is how we move it out of the parent function location. So each term in that quadratic equation will control some type of movement on the parabola. Yesterday we explored changing the vertex and the vertex form. So we were moving it out of that origin location. Other aspects of the standard form will do the same. We have talked about reflections. What we're doing is creating a mirror image. So if we have our parent function in blue, if we reflect it over the x-axis, we will create an image in red. The value of a, which is the coefficient of your quadratic term, does control the reflection aspect. So if a is less than 0, which means it's negative, we're reflecting it over a horizontal line. And it's not always the x-axis. It can be any horizontal line in the coordinate plane. In this particular example, because we're reflecting it over the x-axis, the vertex actually stays in its same position. But instead of the blue graph having a minimum value, when we reflect it to create the red image, now we have a maximum value. So the turning point is now the highest point on the graph. If we perform a dilation on our parent function, we're either stretching or compressing our graph. So again, you can see in the picture, the blue value is our parent function. We're going to examine the absolute value of a. So this doesn't matter if it's positive or negative, but once it becomes greater than 1, we're taking our parabola and making it taller and thinner. So we can see with this green function, when we change the value of a from 1 to 4, it did become much taller. If the absolute value of a falls between 0 and 1, so we're talking fractional values, our parabola is going to kind of compress and become wider. And that's what we're seeing with the red function. The value of a changed from 1 to 1/4, and we can see how much wider it is. When we perform a translation, we are sliding the graph to a new location. So if we start with the parent function, y equals x squared, and we add some amount to it, and I made a note that this is outside the function. This is separate from x squared. What we're doing is moving the parabola either up or down. So if the value of k is 4, this is going to slide the graph up 4 units. So positive, it moves up. If instead it was -4, that would tell me to slide the graph down 4 units. We can also slide our graph left and right. Neither one of these in the diagram are the parent function. We know the vertex would be located at 0, 0. So the format to move it left and right occurs inside the function. Notice it's inside the parentheses with the x. When I see that setup, I know that I'm sliding it left or right. Yesterday with vertex form, we said, remember that x lies to you. So x minus 4 actually moves the graph 4 units to the right. So we're moving in a positive direction. And if you see x plus 2, again, it's lying to you. We're actually moving it 2 units left towards the negative side of the number line. The linear term, b, x to the first power, is going to shift your axis of symmetry away from the y-axis, which is where the parent function is located. So the parent function isn't on here, but we know that the turning point would be here at the origin. As you change the linear term, positive and negative, notice in the green function, it's moving a little bit to the right and down, and then in the purple, continues. If you look at all these vertices, they're actually moving in a parabolic shape. So if we change the value from positive to negative and negative to positive, we would also be moving it this way. So it's traveling along a smooth curve. We talked about the constant c yesterday. This is going to represent my y-intercept, so I should automatically know where my parabola will cross the y-axis. So as long as your quadratic is in standard form, that ordered pair should be apparent right away, and it's something that you can extract right from the equation. The y-intercept can occur anywhere on the parabola. It doesn't have to be the turning point. It doesn't have to be the last point on one of the sides of the parabola. It can be anywhere. Tonight's homework is number 112. It'll say transforming quadratic equations, and there are 6 problems. If you have any questions going through this assignment, please make sure you contact me. Otherwise, have a great day.